A diplexer is a filter which has one input and two outputs, and those two outputs individually have separate frequency responses. Now you could say, well, wait a minute, I can do that just by splitting the signal and having different filters. But there's no splitter here. What happens is that everything in this passband goes this way, and everything in this passband goes this way. So I get all the power in this passband going out this way, and I get all the power associated with this passband going out this way. Whereas if I used a splitter first, I would be down by 3 dB on each one of these ports, and then I would have the filter responses and whatever insertion loss was associated with the filters. So each one of these would be down by 3 dB. So this is typically a horrible idea because of that loss associated with the splitter. Instead, what you do is you design the filters so that when you put them in parallel, the reflection coefficient is 0. And that's what defines a good diplexer. Why do you use a diplexer? Well, aside from this issue with the insertion loss, this is also a convenient way to, for example, eliminate reflections in mixers. When we talk about frequency conversion, we will point out that a mixer, which has RF coming in and perhaps an LO driving the mixer, will have a ton of products here at the output that we don't want. So what's common to do is to put a diplexer in there. And if we want the low pass response, we terminate this into a resistor, as I've shown here, and we just take this one. And that way there's no reflection. Anything that would normally be reflected from whatever follows the diplexer is eliminated. And eliminating that reflection cleans up the response by it. So diplexers are frequently seen in RF circuits, often following mixers for exactly this reason. It gives us a way to safely dissipate the power associated with frequencies that we're not interested in. Now if we want a high pass diplexer, all we would do is we'd move this resistor over to the low pass output and take the high pass output. So very straightforward. Now the textbook explains that the simplest way to create this particular structure is as follows. This is the simplest low-pass diplexer I know of. Looks like this, where this is the input and this is the output. So the output is the low-pass part, and we achieve that simply by having a series inductance and a parallel capacitance. This in effect is a bias T. Is another name that this goes by. Bias T's are used for several things. Low-pass diplexer responses is one. And then we see that this is essentially the high-pass output, and then we're terminating that into this resistor. So this is a simple way to create a low-pass diplexer. You can imagine that the associated high-pass diplexer would look like this. And then that would be the output. All right, so very simple idea. And then we can come up with much more complicated diplexers that have better responses simply by using more stages here, just as we did with the single output filters that we've just considered. And I'll point out that this is just a diplexer, has two outputs. We can also design multiplexers which have many outputs, each one of these outputs having a different frequency response and having the property that any frequency content that shows here will end up full strength in the desired channel, and we don't have any splitting losses.